Yeah. Hello everyone. Disha Kansara here, and my SEP ID is 60001198003. And today I'm going to explain the integrator using OPAM and its frequency response. We implement also the frequency response and phase response of this. So yeah, this is my basic circuit diagram of the integrator. So it is the op-amp integrator circuit which produce the output voltage, which is a proportional to the area and conducted the under the waveform. The ideal op-amp integrator is uses the capacitor which connected between the output and the op-amp inverting input terminal. The negative feedback of the inverting input terminal which ensures that the node X here where it held the ground potential, and if the input voltage is 0, there will be no current through the input resistance Rin. So the capacitor is uncharged and hence the output voltage is ideally 0. If the constant positive voltage DC which is applied to the input of the integrating amplifier, the output voltage will fall negative at the linear rate in an attempt to keep the inverting terminal at the ground potential, and a constant negative voltage at the input result in a linear rising of voltage at the output, and the rate of change of output voltage is proportional to the value of applied input voltage. So this is the short introduction of the integrator circuit. So now I calculate so this is my calculations of the integrator. So I consider the fa 1 kilohertz, fb is 10 kilohertz, and I assuming the cf is 10 nano farad. So my fa is 1 by 2 pi f into cf. Therefore the rf is my 1 by 2 pi f 2 pi fa into cf. So which is my rf is 16 kilo ohms, and now my fb is 1 by 2 pi r1 cf. So my r1 is equal to 1 by 2 pi fb into cf. So my r1 is 1.6 kilo ohms, and my r comp resistor where r1 is parallel to rf, which is 1.5k. So I got the all resistors capacitors value. So now I am going to implement the integrator here. So first of all, I select the op07 op amp. I select here. Then now I'm going to select the resistors. So I need a 3 resistors here. One I connect here, the another one is here, and the other one is here. So yeah, this is my circuit, and I also want a capacitor. So I connecting this, and now I'm select a DC voltage source. So I connected in here, and here. So yeah, and now all these components I connect with the wire. I need a ground also. So here in input and the common ground in the voltage source. So I connect all this with the wire. Yeah. Yeah. So I connected it with the wire. Now I'm going to label it. Here I'm labeling VCC. I forgot to connect here. Yeah. So yeah. So this is my V out, and this is my VEE. This is my VCC. And this is my VEE. So I labeled it here. First of all, I move here, and this I move here. Yeah. So this is my RF. So this is my RF. This is my CF. This is my R1. And this is I labeled as R2, let's say. Now I'm going to value all this. First of all, I give this as a 15 volts, plus and minus 15 volts. My RF is 16K. My CF I assumed 10 nanofarad, and my R1 is 1.6K, and my R2 is 1.5K. I give your input as a AC 1 and 1K here. Let's say input is my 1K. Yeah. To see first of all the frequency response, we see the frequency response. Here I am giving a AC analysis. I am selecting decade. I give it here, let's say number of points per decade is 10. Then my frequency is 100 hertz, and start and stop frequency let's say 10K. So yeah, let's say the frequency response. Yeah, so this is my frequency response, where this dark blue line is my frequency response, and the dotted blue line, you can see it is my phase response. uh, I'll show it here in a grid lines. View in a grid lines. Yeah. So this is my response, frequency response. Now we can see for the sine wave here, output for the sine wave, where I select DC is 0, my amplitude is 1 volt, my frequency let's say 500. Okay, and I added the simulation command where my transient is, let's say, stop time is 100 ms, and I'm run my simulation. Yeah, so this is my output waveform where my V out is around 8.82 volts, and I select the 1 volt in a input volt. So this is my waveform for sine wave, and yeah, to see the waveforms in pulse. So here you can, let's say, -1, 1. My T delay is 1 TP, sorry, 1 T. Then my T rise is, let's say, 0.5 ms. This is T fall is my also 0.5 ms. Then my T on is 1 period, and T period where my, let's say, 1. So I select this, and I also change this transient time. Yeah, so I return it here, where is, let's say, 10 ms, then 1 micro. I run it. Yeah, so here my input is in triangular wave and my output is in sine wave, the little spike here. So here my input triangular wave is around 1 volt, which is 2 volt peak to peak, and here my output is around 5 5.845 like this, which is a sine wave. So this is my second waveform, third waveform, and now to see uh, yeah, I'm changing here first of all. Let's say it is 1 P, then 1, then 0.5 M, and 1 O. And I'm change this transient time. Let's say your 20 milliseconds, and I run this. So yeah, here my input is in a square wave, where it is 1 volt, and the output is around the 9.2 volts, which is in a sign of spike. So yeah, this is my last output of the integrator. So this is my integrator circuit, and yeah, I already made this circuit over here. So this is my another calculations for the another frequencies, different frequencies, where in FA 1 kilohertz I got V out is 13.7 and my gain is around 6.8, and gain in dB is my 16.76, where my FB, which is 10 kilohertz, and in this my V out is 1.9, and my gain is 0.95, where my gain in dB is minus 0.91. So this is my another calculations, and this is my frequency response and phase response of this. Okay, so thank you.